Check. Okay, welcome to the fifth class meeting. So we stopped around here after we derived the objective function. So our optimization problem has the mean squared error as the objective function. And the mean squared error was originally defined as what? The case symbol and the case outputs mean squared error. And this symbol estimation error is now transformed to a finite length interval integration in terms of the power spectral density of the data sequence M of F and the vectorized Fourier transform of the received waveform and vectorized Fourier transform of the overall transmit pulse and 2D power spectral density of the received signal, R of F, which is the summation of the possibly additive white Gaussian noises, additive cyclostationary noises 2D PSD, and the 2D PSD of the desired component. And this happens a lot in communications and signal processing. So let me kind of remind you the simplest signal model that results in almost the same form as this one. Suppose you have Z, let me see, not Z, what is better? Okay, let me say Y. What was the output? Okay, output was Z of T. This is very confusing. Okay, I'm going to use Y. So suppose you have a vector signal model. So your observation is a random vector Y complex valued. And suppose your desired signal component is B times some P vector. And P is of the same length as Y, and plus N, where N is the additive noise, where B has zero mean, and let's say B square equals for everything simple M, just for convenience, and let N, the additive noise, also zero mean vector with correlation matrix R sub N. Got it? Now, given this, the question is find W that minimizes the mean squared error defined as B minus W Hermitian transpose Y modulus squared. Got it? So this could be a very viable QE problem in most of the, at least the Midwest US state universities like Purdue, Ohio State, UIUC, U of Michigan, blah, blah, blah. And let's solve it first because this is so important and so fundamental problem. Got it? So here, be careful. B is random. P is not. P is assumed known constant vector. N is a random vector independent of B, or at least uncorrelated when they are both B and N are zero mean random quantities. Got it? Now, you do the same procedure as we did for our problem. So let's expand it. Expectation of B squared minus B times, 2 real part of B conjugate W Hermitian Y plus W Hermitian Y squared. Got it? So this is just a simple expansion of a complex random variable, right? Let's view this enclosed part as complex number, then you have this one, right? This shouldn't be difficult. And then we have m minus 2 times real of, and we remind y equals bp plus n. So we have what? mp, am I right? Plus W Hermitian, what is y? mpp Hermitian transpose plus Rnw. Ready? So this is the mean squared error. And given that we want to minimize this value by so-called finding the optimal W. And let's compare everything term by term to make everything simple. Let me see. Yeah, there is some scaling problem because of the integration, but you see there is one-to-one correspondence. So here we have WRW that appears here, right? And R is the correlation matrix of the received signal, not only the interference component, but also the desired component. And we have the negative 2 times real part of the desired component and let me see, W, I missed the W, okay? So let me see, W Hermitian, yeah. So M times W Hermitian P, so M times W Hermitian P, right? Of course, there is some scaling problem with 1 over capital T, but basically, they have exactly the same form. Got it? Now, what you want to do is that we want to apply derivative with respect to each element of W. The problem is that many of you never seen this kind of notation. So this is a derivative of epsilon with respect to the W conjugate vector. And if all the terms were real, there is no 2 times real part. So you know how to differentiate a quadratic function of W with respect to W vector. You know that. The problem here is that you need the so-called the Wortinger calculus. That is for the complex derivative for the so-called analytic functions you learned in engineering mathematics. Probably many of you have taken that course with Kreisig famous textbook, and it has the complex function chapter starting with the definition of analytic function. So it's different from analytic signal given a real valued bandpass signal. They have remote relation if you just far-fetch it, but analytic function as some complex complex valued function is different from that analytic part of a complex real valued bandpass signal. So if you don't remember what I'm talking about right now, after the class meeting, you consult your old textbook or at least try to find Wikipedia. It has a very nice page about the analytic functions. And find what's the meaning of analyticity, what Riemann and Cauchy loved it. And it's all related to the first order approximation of a differentiable function. And that would be quite different extension of what you know. For example, suppose you have a real valued function of real variable. What is the meaning of differentiability of this function? You say that, hey, derivative exists at a point, then it's differentiable at some point. If it's differentiable, for example, on an entire real line, it's a differentiable function. That is too naive, okay? Actually, differentiation is for first order approximation of this function, which means that you want to do something like this. Got it? So at x0, you want to approximate this function with an affine function of x. If you plug in x0 here, then it cancels, and you have f of x0 equals f of x0. However, if x is not equal to x0, but close enough to x, then you want to claim this. And here, if such a claim is possible with a unique number a, then it is called differentiable at x0. Got it? So your naive high school or just highly unfocused, unstudied undergraduate calculus memory must be deleted, okay? Whenever you see differentiation, you always remember that, hey, I want to approximate this one using an affine function. If you apply derivative twice, then some quadratic function. 3 times, some cubic function, something like that. Got it? So uniqueness, not only the existence, uniqueness of this coefficient A is the core of the differentiability at x0. Same thing. Suppose you have a function, complex valued or real valued. So here, f r into r, this is your high school. Now f c into c, which means that you have a complex value, the function of complex number. Let's call fz, okay? Now you want to do almost the same thing as you've done in real function of real argument. Again, you have an affine function of z now. If this a exists, it could be a complex number because f is, in general, a complex valued signal. If a uniquely exists, then f is called an analytical function or analytic. Got it? So it's all related to differentiation and existence of an affine approximation, unique affine approximation. Got it? So here, let me just simply go back and say that this objective function is fortunately analytic function. And the derivative, partial derivative with respect to W and partial derivative with respect to W conjugate, both gives you the same thing, but this derivative with respect to W conjugate give you a much compact form of the result, and that result is very similar to what you already know for real valued quadratic functions partial derivative. And that is what? 2 times M PP Hermitian Rn W minus 2 times MP. Got it? So this M is constant, so it's gone, right? And this part, real part of something, the real part operation is gone. Very good, because this is so cumbersome. Because real part of some complex number involves conjugation of the argument, and it's gone. Got it? And as if this is not there from the beginning, and W Hermitian is W transpose in your real valued person. So just simply it's 2 times M times P after partial derivative with respect to W conjugate. And again, you already know, given a square symmetric matrix, pre and post multiplied by some vector and differentiated, you know that that is what? 2 times this square matrix times this vector. Exactly the same. Right? Interestingly, many textbooks never talk about the derivative of this one. They just say that, hey, just simply we get this. That is wrong, okay? You need at least the knowledge about this analytic function and the derivative with respect to W conjugate. But anyway, this Wortinger calculus looks complicated, but it's more than what I just told you. However, applied to our case, it's just very simple. Our result is very similar to what we already know with real valued matrices and vectors and quadratic forms. Got it? Anyway, so if we want to minimize this epsilon, the objective function, we differentiate with respect to W conjugate and set equals 0. This equals 0. Then what? Just simply W optimal equals this correlation matrix inverse times M times P, as you already know, right? And that is exactly what we are going to do with this one. And you may say that, why? And let's see this one. So we have an uncountable infinite sum, even though we have a finite interval. However, our integrand at each f is what? Is in this form. Now suppose we can minimize our integrand at each f without affecting other optimizations in different f values. Then we can minimize at each f to get the optimal value. Actually, this idea appeared amazingly in the entrance exam of post-tech undergraduate course long ago. Let me give you a simplified version of that problem, and you'll be amazed. Our math department professor was so crazy at that time. Given f defined on 0, 1, 2, 0, 1. Ready? What does this mean? its domain is interval 0, 1. Its range is 0, 1, right? Given f. Find f that maximizes if I remember correctly. Yeah. Too simple, right? Just 2 lines, even though I wrote it in 3 lines, actually just 2 lines. And at that time, it's around 15 years ago, I remember, we had in our entrance exam around 3 math problems and 3 some science and science problems, depending on the choice of subjects. Many students have chosen maths and physics. Some students have chosen maths and biology, maths and chemistry, maths and what? No geoscience. maths and what? 생물, 화생. Yeah. Physics, chemistry, biology. Anyway, so 3 problems and 3 problems. So this problem was around 1/6 of the entrance exam. Unfortunately, when I interviewed the students, I usually interview around 20 students per day. Only 2 students got this one. Of course, there were other problems they could solve. At that time, if a student solved 2 out of 3 math problems perfectly, they are very, very good. Most of the students just solve 1.5 problems. Anyway, so try this. Solve it right now. Right now. Anybody? I've given you already a big hint, right? So you could be much easily solve this problem because I've given you a hint. When I talk about how to optimize, how to minimize this epsilon in equation 29. So after I saw this problem, I asked my graduate students to solve this one in the exam, actually. I put exactly Control C and Control V this problem in one of the probably final exam or some third midterm exam. At that time, I was so harsh and midterm, 3 midterms and 1 final, even in graduate courses. Anyway, so anybody? So let me just tell you. So here, you view this as what? Summation of infinite uncountably or approximately summation of many terms. You may divide it into something like this, right? And k plus 1, something like that, and k from 0 to n minus 1, something like that, right? And fx minus x dx so far is exactly equal. You just divide the interval into finite numbers. And then you approximate like 1 over n summation fx k xk like this, right? And k ranges from 0 to n minus 1, right? Now it's approximately like this. And you want to maximize. What is this? This looks like that, right? So if your x of k is around here up to 1/2, what would be the best strategy to assign a value, f of xk, to maximize this one, right? Your maximization can be performed term by term. That is the key. But unfortunately, high schoolers in Korea never exposed to so-called Bernoulli's Brachistochrone problem, which is the problem of minimum time elapsed, something like that. So they never heard of it. Last time I told you LH, and you have frictionless surface you design, and there is a gravitational uniform field. And what is the shape of the slope that minimizes an object that is stationary here, and from time zero, it's affected by the gravity and arrives this point. And it's a very famous so-called Brachistochrone problem. In Latin, Brachistochrone, and in English, minimum time lapsed, something like that. And it's a cycloid. That's very famous problem. You just type in minimum time cycloid Bernoulli, and then you will find a lot of pages related to optimal control and calculus of variations. But among calculus of variations problem, this kind of designing a curve is the simplest because it can be just done term by term. So if the value is x is less than 1/2, you choose 1, right? So this value and this x is farthest. And if x is between these two numbers, then you choose 0. So you've just found a Riemann integral, because in high school, students are only taught the Riemann integral. So Riemann integrable function that gives the maximum of this value. So the f of x equals 1 for 0 to 1/2. And this is inclusive or exclusive. It doesn't matter, as you know. Anyway, something like this. But this is not that important. It's just single point, right? Because it's anyway Riemann integrable. Got it? And you ask your friends whether they can solve this one or not. It's very interesting. Fortunately, since I taught something similar in the 649, the estimation detection theory course already during that semester, many students got this problem correct. So I was happy. But anyway, so the same thing happens here. If you take this integral carefully, and suppose you just want to optimize W, not S, that is hidden here. S is inside this P, because P of T is the convolution of H of T and S of T. Just let's focus on optimizing W first. And you may say why, but just think about that. Then you can just simply minimize this integrand at each f by finding optimal W. And that is so easy. Now, let me justify why we do this. First, we want to minimize. So I'm first claiming that the problem can be put into this double minimization problem. Before, our problem was what? Problem was minimizing this epsilon with respect to W of T and S of T subject to this one, right? And here, this is also rewritten in terms of the vectorized Fourier transforms like this. It can be done. You should be easily do this. Ready? Now, there is one step missing, but anyway, it's like minimize with respect to W and S of epsilon subject to equation 32. This is equation 30. Got it? Not 30, 29. Sorry, 29. Got it? And this single criterion optimization problem with two decision parameters, fortunately, can be put into this one. And this is, interestingly, a simple trick and very important trick, but not appearing in many textbooks on optimizations. I believe it's too obvious. It's too obvious, so people never seriously teach this one. But think about this one. Here goes the simplified version. Suppose f is a real valued function of two variables, x and y. So you have f of x comma y. Suppose you want to minimize this function value with respect to x and y, subject to x comma y in some constraint set. This is standard optimization problem in R2, right? With some abstract constraint set. And this one can be visualized like this. Suppose this is the constraint set omega, and horizontal and vertical axes represent x and y. Now, you want to find a pair x comma y that has very small number. And here goes the idea. Suppose we divide this omega into very, very narrow strips. Vertically sliced. Now, what you do is that you divide this omega into union of omega k, the case constraint set, and also two different constraint sets are mutually exclusive. This is a very important trick when you do optimization. And actually, this is so obvious, even though it's mathematically non-friendly, but too obvious. Suppose you want to minimize function in a set. And now, what you do is that you divide the search space. It's like you lost your cell phone. I lost my cell phone, where it is? Okay, let me think about it. I never left today the post-tech campus. It's either in my dorm, it's either in my classroom, it's either in my restaurant, something, right? And you search, same thing. So you can always divide the constraint set in any so-called into partitions. Each one is called a partition. No, this is not good. A partition means that this is partition, okay? So collection of subsets, exclusive subsets over a set is called a partition. Got it? So it's really divided. You have a dish that is broken. And if you put them together, it becomes a dish. Got it? So here, among many different partitions, let's think about this type of partition. Now, what you do is that you find some point x1, y1 in omega 1 that minimizes this value. Okay? Suppose you can do that. And also for omega 2, the second subset, you find x2, y2 that minimizes the value. Got it? Then, assuming here in this figure we have finitely many subsets, we will have now how many? Finitely many. Let's say we have capital K subsets. Got it? Then we have capital K candidates as our optimal solution. And among them, we may find the pair of x comma y that gives us the minimum function value, right? So we may rewrite this one in this form. We can either minimize with respect to x first or y first, it doesn't matter. Be careful, subject to what? X in omega y. Here, omega sub y means that the set of all x comma y's with y equals y. Something like that. Here, capital omega sub y means every possible y in the constraint set. So exactly, let me see. Not this one, sorry. Let me use y first, x. So y, x, x, x. And we have x. Got it? So here, this is so-called the inner optimization. And this is called outer optimization problem. Got it? It's inside the entire problem. Got it? This is inner optimization, and this is outer optimization. And here, what does this x omega sub x means? Here, given x, you have what? An infinitesimally narrow strip, right? X comma y's. That means this omega sub x, given x, right? So given x, you minimize this. And after you have found the optimal y's for each x, you do the outer minimization for every possible x in omega sub capital X. Means that probably from here to there. Ready? So in this problem, this set would be omega x. Ready? So for each x in omega sub capital X, you have a strip, right? And on each strip, you minimize that one, and done. And you do the same thing for alternative double minimization. Got it? By slicing the subset, the constraint set, into this parallel lines parallel to the x-axis. These two are very typical partition of the constraint set, right? You can even do some partitioning with these slanted lines, and even you can do any partition if your inner optimization and then outer optimization is easy on each set. So what you do is that you introduce a partition of the constraint set that allows you to do this conversion to double minimization and solving inner and outer optimization easily. So it's your choice. You should be able to find some partition that allows easily solving the problem. Got it? And here, fortunately, your original problem has two decision variables or parameters and a constraint set. However, given S, suppose you want to minimize W. And interestingly, here in this constraint set, the constraint set is only dependent on S. So if you choose S out, plug S out, and put it in the outer minimization, inner minimization is an unconstrained problem. And that's very nice. That's why here we put this unconstrained minimization. This is unconstrained. Because unconstrained, especially this quadratic minimization, its solution is well known and analytically given. Very nice. Ready? So there are many choices in converting a multiple optimization problem into nested, because in this case, we only have two inner and outer. However, it could be nested into more than two. Outer, inner one, inner two, inner three, inner four, inner million, if you want. In inner millions optimization problem, if you want. If you find that's easy, that makes everything easy for you to solve the problem. Got it? So here, this is one of the most important tricks you will see again and again and again and again in the series of papers. And it's too obvious, right? It's just so simple. However, as I told you, it does not appear in most of the introductory optimization problems. I don't know why. They usually put, probably the professors are so smart who wrote the textbook, and they usually put this complicated problem, so-called minimax problem. They do something like this and have a lot of inequalities and min-max or max-min problems and relation between the minimized min-max problem and maximized max-min problem and inequality, and if whenever equality holds, blah, blah, blah. Of course, that's important. However, this double minimization with respect to two variables can be put into this form, and it's very important. By the way, you've seen this already in your multivariable calculus when you were properly taught that subject. Unfortunately, what I have found is that in Korea, many professors, math professors, they are not that eager to teach freshmen. So they just say, okay, here goes the double integration. Okay, x comma y in omega. And this can be something like this. So obvious. It's not obvious, actually. Okay? This corresponds to double minimization in our problem with single objective and two parameters. This is so-called nested inner integration and outer integration. And if you are taught properly, your math professor have shown this not as an obvious result that always holds, but probably put some remark as the theorem. Under certain conditions, blah, 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 this can be computed as this one. And even these results usually have a name as Fubini's theorem or something. Got it? So idea is almost the same. So you see the parallelism between this conversion of an optimization problem with more than two decision parameters into double or sometimes triple or quadruple minimizations, nested version, with the multiple integration in R to the n. So if we generalize this one, then we have some multiple integration R to the n something like this. And we convert this multiple integration, actually, properly speaking, multiple Riemann integration as a integration, nested integration, and single variable Riemann integral or something like that, right? Anyway, so everyone got me? I hope so. Anyway, by the way, when we convert the constraint that is written this way and that one, we introduce here A of f. That is appearing here. So A of f is simply the S of f, the vectorized Fourier transform of the transmit pulse norm squared at specific frequency offset f. Why do we do this? Because it is useful when we do the outer minimization. So you will see why I've done this. Anyway, so inner minimization is now an unconstrained optimization problem that has very simple solution. So here goes our result. Okay, so we have, as I told you, just received signals correlation matrix inverse times this M of ft times P of f. So we have this. By the way, from here to that one, this is also a very well-known conversion. So even I didn't say much thing. And that is also related to this problem. Of course, many textbooks in communications and signal processing have this problem with all real valued, but derivation is almost the same because even if the variables vectors are complex valued, the function is analytical. So our general derivative and some other things you've already known is just extended. Okay, probably you remember something like this. What is x to the n differentiated n times? Then you know, right? N minus 1, blah, blah, blah. And probably you also remember if you want, let me use m, right? Z to the n, here z is a complex number, variable, differentiated m times, and it has the same form, right? Depending on what is m. Why this is so? That is all related to what you learned in complex functions and variables and all related to analytical signal and those Cauchy-Riemann conditions. If you don't remember that, probably you didn't study hard, as I didn't when I was a sophomore, okay? Even though I got A+ in that engineering mathematics B, we had engineering mathematics A, B, and C. And interestingly, engineering mathematics C was the mandatory subject in our freshman second semester. Crazy curriculum. But anyway, so what you know, like log 1 plus z differentiated, what is this one? You already know, right? Why this holds? Why this holds? Because logarithmic function is an analytical function. If I too much simplify why this holds. You know this, right? For real valued function, real valued logarithmic function, right? This extends to that one. And why? Because logarithmic function is turned out to be an analytic function. Anyway, so you have found from here something like this. In order to make everything simple, let's forget about m and everything. Let's say m equals 1 in the previous one. Then your objective function is And all the things are real valued. All real valued. Then you have 2 times W transpose P plus P transpose Rn 2 times W, something like this. So if you differentiate with respect to W, then you have 2 times P transpose R, W transpose W minus W minus P. And if you set this to 0, implies W opt equals PP transpose plus R inverse P, right? This is very, very famous result with all real valued things. And here, this matrix inverse is also rewritten using so-called matrix inversion lemma. There are a lot of versions, very general and very simplified versions of matrix inversion lemma. And the simplest one is related to some invertible matrix times UV transpose. Okay? Historically, this inverse, some invertible function A plus rank 1 matrix. Here we assume A is symmetrical, invertible, right? And U and V are real valued, same length vector. And the first persons actually, who found a matrix inversion lemma for this special matrix inverse are Sherman and Morrison. So it's called Sherman-Morrison formula. But it's simply the most general versions, extreme simplified version. So if you just Google or Wikipedia the matrix inversion lemma, even Sherman-Morrison formula may not appear. They say that it's too obvious. Okay, but anyway, so what is this one in terms of A inverse and this U and V? Anybody? If I remember correctly, we have this one, and let me see, is it something like that? Yeah, even I do not exactly remember. Probably this is plus. Yeah, something like this. I believe so. Yeah. How to check the validity of this one? It may contain an error. I do not quite remember. Okay, I'm no longer a graduate student. So you are responsible to check. So how do you do that? You just multiply this one with the argument here, A plus UV transpose. Then if you get identity matrix, that is true. If it is not, some part is wrong. I'm not sure. You'll find it. Got it? And here, even this is simpler. U equals V equals P, right? And A equals R. So let's do the computation. We have, Rn, if I remember correctly, Rn. Yeah, Rn inverse minus 1 plus P Rn inverse P, Rn inverse P, P transpose Rn inverse. By the way, be careful. This is a matrix, right? This is a matrix. So you must have matrices in each term. Is it a matrix? Yes. Is it a matrix? Yes. Because if you multiply A inverse U, you have what? A vector. If you multiply V transpose A inverse, you have a row. So again, you have rank 1 matrix here. This is rank 1. because it's an outer product. And in the denominator, you have scalar 1, and you have a kind of quadratic form type thing. This is a scalar. Got it? Sometimes it could be 0 in some cases. That is too bad, because in that case, this entire equivalent formula does not work. So be careful. When you use this formula, you should be careful. You never have the denominator equal to 0. Okay? Anyway, so if I remember correctly, we have this one. And it's not yet completely done, because we can still expand, right? And group together. So let's have this common denominator. And what else do we have? 1 plus P transpose Rn inverse P times Rn inverse P minus Rn inverse P, P transpose Rn inverse P. Am I right? Am I right or wrong? I believe I'm right. Yeah. And anybody noticed some simplification? When I first saw this, when I was taking the optimization, introduction to optimization, I said, hey, what kind of simplification can be done? But the thing is that this is scalar, okay? Scalar times vector can be exchanged. It's commutative, right? 5 times the vector v is same as vector v times 5. So the numerator can be rewritten this way. What do you want? Sorry about that. Got it? So we have this second and third terms cancel each other. Got it? See that? Here, this is scalar. I know your frustration. I had that in 1996 spring semester when I was a first year, second semester graduate student. And at that time, professor was just write everything very obviously. And I got frustrated. Got it? So whenever you see quadratic form, some P transpose R P, then remember it's a scalar. So it could be enclosed into inside a parenthesis and moved back and forth, right? So after you expand, just a second, something's wrong, Rn inverse. Sorry about that, Rn inverse P, right? So first term is Rn inverse P. Yeah, second and third terms cancel out. Got it? So you have vector equals vector divided by a scalar. Got it? So the difference is that before W was written as R inverse P, and now what is R? What is R? R is the correlation matrix of the received signal. Now it can be rewritten. This entire result says that optimal W can be rewritten as what? The correlation matrix of interference, unwanted signal, inverse times P, properly scaled by a scalar. Got it? They are the same, amazingly. See that? We have this term that only affects here. right? So our optimal received vector W opt can be written as received correlation matrix inverse times our desired signal vector P, or our received signals, unwanted signals correlation matrix inverse times desired signal properly scaled by this denominator. You must remember this. This will ever appear in your research if you are doing any type of mean squared error minimization. This is so fundamental. It's just estimation theory 101 material. Got it? And also this expansion, this simplest form of matrix inversion lemma, named Sherman-Morrison formula, must be remembered. Okay? Anyway, so what is good? We apply just that result with some scaling. The difference is that we have capital M of Ft and we have 1 over capital T, but they are almost the same. Now, our objective is what? After we find W, we want to find S, right? If we can rewrite W, the minimized inner optimization's objective function in terms of only S of F, it would be great. So what we do is that we convert this one, not only this using Sherman-Morrison formula, but also using only S without W, because W is plugged in, right? W is disappear. So we, after plugging in to this one, our W opt of F, we have amazingly this objective function for the outer minimization, only for the minimization of S. See that? This epsilon is the same epsilon, except that now in the receiver, we use minimum mean squared error receive waveform, whatever S we have. If S is changed, our W automatically changed, our H is changed, our W is automatically changed here. And again, it's a finite interval integration. Now with what? No W, but here S and H. See that? Here C never appeared, but here it is defined. C is the interference correlation matrix inverse times H of F and H of F Hermitian. Here, H of capital F is defined as a diagonal matrix of H of F, the vectorized Fourier transform of the channel impulse response. Got it? You can show this without much difficulty. By the way, you may say that, Professor, you say without much difficulty, but it's difficult. I know that. In the next paper, not journal 8, but journal, is it 16 or something? Yeah, 18 actually. So our original paper list has this many, but I will jump from this to that. Okay, that's good. And even before I jump to journal version 18, I will talk about this old paper by Gardner and Franks. Okay. And you know, interesting thing, Dr. Gardner was a graduate student of University of Massachusetts Amherst, where I served as a professor. Long time after he graduated and became a professor at University of Santa Barbara or something. By the way, Dr. Franks was his advisor. This is advisor, professor. So they jointly published this when I was 4 years old. And amazingly, when I published my paper, my best paper, when I was a graduate student, the best paper of my graduate period, I never thought that I would do some research related to what they did. Even though I presented my result, actually, he, as a professor emeritus, was there when I was presenting my job interview, the job interview seminar. And he said, it's very interesting and sounds like related to what I've done long ago, something like that. And actually, he had the office next to my office, my first office. But he rarely came to his office because he was professor emeritus. Anyway, so they published this one when I was a baby, toddler. And I was shocked, actually. I was doing my research in order to resolve some problem which never solved, even though it was the only problem my advisor asked me to do, because he never asked me to do something during my entire graduate period. He just asked one task, but I didn't complete that one when I was a graduate student. So I kind of have a quest to solve that, and suddenly found that, hey, Dr. Franks, I'm reading your paper. Anyway, it's very interesting. And here, if you want to, because we are running out of time, if you want to jump around a week, then read this one, especially this sections titled Harmonic Series Representation and Translation Series Representation. Actually, these two terms are coined by these two authors. And now it's a standard terminology in cyclostationarity society. However, this society is very small. And these days, I'm using my Google, not Google Scholar, what is the Google service. So I set that one long ago, around 20 years ago, when Google was initially launched, set cyclostationarity. And Google is still sending me an email periodically with new results, new published results. And interestingly, most of the results containing cyclostationarity is now in mechanics. They are handling vibrations, mechanical vibrations. Consider that you have an axis rotating very fast. Then you have some defect. Then you will see some periodic bump, right? But your sensing system may have some noise. And your observation looks like cyclostationary random process. So interestingly, vibrations are the key words related to cyclostationarity these days, but still sometimes I see some communications and signal processing papers talking about that. Anyway, so let me go back and continue. So now our problem is what? Is simplified to our auto-optimization problem without W of F. And that problem is like this. We want to find S subject to this one. And here A is what? A is S of F magnitude squared. And as I told you last time, there is a subtlety about the length of this vector and size of these matrices. Because depending on F, the offset used to convert the ordinary Fourier transform to a vectorized Fourier transform, you had xi, but you have offset F for in order to sample this Fourier transform, right? And due to the assumption of band limitedness of our entire signal and processes, depending on this bandwidth and whether it is integer multiple of 1 over 2t or not, in many cases, these vectors and matrices are of varying size, depending on F. Sometimes it's 1 by 1. Sometimes it's 2 by 1, something like that. So be careful. Let me just give you an idea using SRRC or RC if you want, raised cosine pulse. And in the raised cosine pulse, we have symbol time capital T, and usually our so-called roll-off factor is related to the bandwidth. This alpha is between 0 and 1, including 2 endpoints. If alpha equals 0, you have a sync pulse. If you have alpha equals 1, your bandwidth is exactly 1 over t in baseband, right? Now, this is converted to, let's say that this is, let's say that S of F, S of J. This is J. Got it? Then, what is S of F? If F equals 0, how many samples you have? You have just one inside the band, just this one. So S of 0 equals, let's say the height is 1. It's length 1 vector. But what if you have F between these 2 points? Then, for example, suppose, what about S of 1 over 2t? Then you not only sample here, but also sample here. And suppose this is raised cosine with height 1, then this is 1/2. So you have 1/2 and 1/2. Right? What if you have the value between these two? S 1 over 2t plus some delta. Then you have some 1/2 minus, let's say, sorry, plus, because here it goes up, some beta of alpha, and 1/2 minus some beta of alpha. Here, beta is not that excess bandwidth. It's some function of alpha, depending on, it would be cosine something, right? And you know that the raised cosine has point symmetry. So if you have increase from 1/2, then you have the same decrease here in F, in the value, right? Something like this. Depending on your offset, this vectorized Fourier transform changes its length. This is very complicated and actually tortured a lot of researchers in this area. And they intentionally avoided this one, saying that, hey, okay, let's assume that we have odd numbers of Nyquist zone so that we have always same length vector, just for convenience. And if it is not handled carefully, they did that. But I didn't like that. So later you will see some other papers how I handled that one and found something interesting. But at this current point, don't be too much frustrated. Because later I also have found that there are ways to handle this variable length problem by putting some strange constraint. So it's like, even though theoretically we have varying sizes of vectors and matrices, just we may fix the length, but in our optimization problems, we may put some constraint that effectively removes signal emission outside the desired band. Later you will see. Anyway, here, so let me a little bit more extend. So here, another idea is this one. See that? Suppose you already have A of F, optimal A of F, or some A of F. So at each F, you know this, then can you minimize that one? Actually, it is true. So what I have done here is that even though the original problem was two decision parameter optimization, I intentionally introduced additional optimization variable that makes auto optimization as a new double minimization problem. So this one is now converted as, even though paper does not say because it's too lengthy, A of f subject to exactly this one. But here, got it? So interestingly, at each f, offset f, we can do minimization given A of f, the norm square of S vector. How? Because see that A is given. I've intentionally put this one and divide by 1. It's like A divided by A, assuming A is not 0. Then what is this one? This is the famous Rayleigh's quotient, even though I mistakenly, this is an amazing mistake, Euler's quotient in my paper, but it's so-called Rayleigh's quotient. This is all related to what? Maximum and minimum eigenvalue of that matrix C. If C is Hermitian symmetrical, positive, semi-definite, then minimum value is 0. Maximum value corresponds to the maximum eigenvalue. So it's like the original two decision parameter problem is transformed into double minimization, and inner is solved, and you have now a single optimization problem, but you intentionally introduce new problem. Actually, that is related to partitioning of the constraint set. See that? Do you see? This problem with that constraint can be viewed as you have some new omega. And this is all S of f, right? F in the Nyquist zone. So among every possible vectorized Fourier transforms of that length, right? You have some constraint set omega for S. Let's say omega S. Now I divide this one into several subsets having the same A of f. So given A of f function, can I find, my question is that, optimal S inside this subset? And actually, it can be done using simple maximization of Rayleigh's, not Euler's. I really cannot understand why reviewers didn't point this out. They just read the equation only, I believe. Got it? So do you see the idea? Partitioning a constraint set cleverly allows you to do some amazing analytic optimization. Got it? Anyway, that's all for today. See you on Wednesday. 공유가 안 되고 있었어요? 뭐예요, 이거? 뭐죠? 큰일인데? 공유가 안 되고 있었으면 뭐 엉망일 텐데. 전혀 녹화. 예, 근데 공유가 안 됐으면 큰일인데. 뭐가 된